I'm going to talk about memory checking. And the background is that at Nexus, we're building a zkVM. So the intention is that we want to do computation. We want to prove to people it's correct computation. And we found out that, so when we implemented like modern techniques for that, folding schemes, Nova, Hypernova, and so forth. And we found that the memory checking that we're doing, I mean, there's a lot of things that slow us down. In particular, dealing with memory was what was slowing us down. So I want to tell you the story of what the issue is there, why we using the wrong technique for checking memory, and then talk about other proposals and some of the more recent techniques that are used for memory checking. And I think one of the themes of what I'll get to is actually something that also came out of Stanford, so like the Mangrove paper using some similar techniques. This doesn't work anymore. Okay, but that I can at least solve. Okay. So the background is so we want to enable people to do computation. So we have a virtual machine. We will give inputs to that, so people can come and use the system and give inputs to that. So they would specify, here's a program, here's an input X, here's another input, auxiliary input W. I will distinguish a little between X and W. So X is public input is something that you explicitly need to check. This is really what the machine is running on. W is an auxiliary input. You may not need to explicitly check W. So that's the distinction between those two inputs. And from that, you will get an output of this computation. Right now, the question is, okay, if you go to the cloud, you do that kind of stuff, right? Then how do you know that this output Y is actually correct, that you are getting what you were intending to compute? Okay, so that's the idea of a zero-knowledge virtual machine, a zkVM. It will also produce not just the output, but also a proof that is the correct output.
Is it actually zero knowledge?
And that is a very good question. So it's a bit of a misnomer, right? That really it's a succinct VM, right? It gives a succinct proof. I think it does happen to be zero knowledge in our case in principle, but also zero knowledge is again, there's a bit of it. What does the definition mean, right? So in general, in zero knowledge, you think of here's one monolithic proof, or here's a proof, right? And that's a zero knowledge proof. We're actually creating a network of computation, right? And then there's also questions is it zero knowledge inside when you have I don't know, a malicious node in that network? Okay, so matching that VM, there should also be a verify algorithm that you can run that will take as input the public data, right? So the program that it needs to check whether it's been computed correctly, the input you explicitly want to verify the output, right? And the proof and decide whether this is a good proof or not, right? So whether you believe this is a correct output or not. And if we look inside the VM, then, in general, I'll use this kind of box here to designate the boundaries of the zkVM, right? So from the outside, it just looks like you're giving some program and some inputs, and you get some output and a proof out, right? And inside, you will have the VM execution. It will produce this kind of execution trace, and actually that's what you feed to a typical zero-knowledge prover that produces the proof. Okay, and I kind of want to give you just the historic picture of proving efficiency, right? Because that's the name of the game here. How efficiently can you construct these proofs here? So what is the historic perspective, right? So zero-knowledge proofs were invented in the 80s, and back then, you had no bounds on the prover, right? That's all the time in the world, exponential time or whatever, fine, right? As long as you could just prove anything, right? Then that was great. And pretty quickly people came up with the notion of hey, maybe we want efficient proofs. And what efficient prove, if you ask somebody who does computational complexity theory, you ask them what is efficient, then that's polynomial times, right? So that was sort of like, if you ever see like old papers talking about efficient provers, that's what they mean, right? And then we can sort of see how the language has shifted over time, right? So I guess in the 90s, people started talking about linear proving time. And typically that would be sort of like a linear number of exponentiation or some other cryptographic operation compared to like maybe Boolean gates or something, right? And if you really want to do fancy efficient stuff, then you would talk about arithmetic circuits, and then sort of like the comparison. And I think over time, we've seen like people getting more and more precise with the language, because sort of like pushing the performance, you have to be more and more precise to sort of like say what is the advantage you're getting, right? So we're talking about now, so like constant number of cryptographic operations per arithmetic circuit gate that you're proving. Maybe we'll sort of like reformulate that with constraint systems instead of arithmetic circuits. That's sort of like the modern language, right? And we'll do something quasi-constant number of field operations rather than cryptographic operations. And then we'll sort of like talk nowadays. I think the game is, can you do a constant number of field operations per CPU cycle? So we're sort of like starting to talk about zkVM language, right? That there's some sort of like notion of cycles that you're proving, and this is the cost per cycle. I think we're moving towards like even more concrete measurements where it's really like trying to do apples to apples comparison. So how many cycles would it take to prove that a cycle is correct? And concretely, how many would it be rather than big O notation? Right? And you can ask, so like in the future, what will so like the end game be? So I put my bet here, right? So people are thinking about like building special purpose hardware for proving computation is correct, right? And then you can't really talk about cycles to cycles anymore, because that wouldn't really compare. And I think like probably we'll have to go into the domain of physics and say what is like really when expressing what we're trying to do. And I guess that is something like energy cost per cycle. I want to show another slide as well with sort of like the historical perspective here, right? So
Actually, maybe a question on that.
Sure.
It's a great vision. I think it's mostly right. But one like concurrent trend is that the most compute-intensive applications that we're running outside of the context of zero knowledge or cryptography aren't really being run on CPUs anymore.
Right.
So this notion of like cycle as the denominator of our overhead measurements.
Yeah. Okay. That I think yeah.
Yeah.
I like that. And I think there's also a bit of a question, right? So there's also a question of which computation is valuable enough that you want to verify it, right?
Yeah.
And I'm guessing, so like, so I would think like financial transactions, I would think, I don't know, maybe there's something medical stuff or defense stuff or something like that. I'm guessing that maybe the most sensitive things are still things that are running on CPUs other than GPUs, right?
Yeah.
So that's an interesting question. Yeah. But point well taken. And it's not something we've not really looked into, like if you want to verify a lot of GPU operations and things like that. Yeah.
I guess my kind of response to that question, kind of hot take response would be that perhaps we could measure like the ratio that it would take to produce like a fruit operation versus the non-fruit one, just to do the operation directly. And then that we will want to see that asymptote to like one, basically.
Yeah.
Energy.
Yeah.
Right.
Yeah, that's I think I like the energy to energy notion. Maybe that's what we should be looking at. Yeah. Okay. Yeah. Okay. So there's some things that we've sort of like researched in the past years have resolved, right? So proof size is something that can be really small. We're talking about like hundreds of a few hundred bytes to prove an arbitrary large and complex computation. Verification time is also something that's solved. Essentially, it takes the cost of reading whatever you want to verify plus a little more, but something which is independent again of the size of the computation. And the remaining bottleneck, right? There's no such thing as a free lunch, and where we're really paying for this lunch is in the proving time, right? So that's sort of like the performance barrier, and it has been for quite a while. But again, we are like, if you look at the historic perspective, we are making progress, right? So I would say, again, back in the 80s, anything would be hard to prove, right? In the 90s, we had like Schnorr protocols and things like that. So that's all like solid identification things and signature schemes. I did my PhD on voting, so that's all like a topic that's near to my heart. And there the game was like the users has an encrypted vote. They are using their browser. They want to prove that it's a valid vote that they have encrypted. And that would take a few minutes, right? And not really good user experience. And the game was really could get down that to a few seconds, right? With a lot of hand engineered proving techniques. And then later I was working in mixed nets. That's all like, now we're talking about like you have like this complexity of like, you have 100,000 ciphertext, a million ciphertext. You want to shuffle them around and commute them and re-randomize them to hide things. And that's what you want to prove, right? So that was considered a big statement and a big computation to prove, right? And so like now we've seen a lot of adoption in the blockchain space, right? Where it's like, kind of prove correctness of Ethereum block computation and things like that. And what we are hoping is that, later on it will be basically everything where you care about security. Okay. And as you may have noticed, then everything is a pretty big computation to prove. So here's like the standard way of doing that, which is that you sort of like try to slice the long computation, right? So you have like the VM, it has an execution trace, it sort of like output something, right? How do you want to prove that? Well, you chop it into smaller bits and prove each of those. And then you sort of like aggregate those proofs and get a proof for the whole computation. And I'm not going to talk so much about the prover network we're building, but essentially that's also the idea that you would distribute the computation of this proof. Okay, and yeah, now I'll do a little bit of notation. Okay, so Paul Valley in 2008 suggested the notion of incrementally verifiable computation. So the idea is you would have, if you have a big computation and you want to sort of like incrementally compute it, then you can, again, you can create proofs for each step of those. And you would sort of like, so you'd have like the function f represents what you want to compute. It takes as input some state, produces some output and feeds that into the next step and so forth, right? And there might be some extra, in every step, there might be some extra auxiliary inputs that you feed into this computation. So, and the vision he had was like, if humanity has like 100-year computation it wants to take, right, you would want to sort of like get going, but once in a while you would want to spit out a proof and see are we still on the right track and is everything going right, or stop the computation. Okay, so the prover here would then basically take, so like the number of which step we are at, right? The input is operating, so like the input, so like the starting point of the whole computation. Okay, and we'll take so like what is the next output, and then it will so like want to prove that is correct. And as part of that, it would so like take the previous proof that the input is correct and the auxiliary data as well, and then it will produce a proof that this step has been executed correctly. So in other words, Z1 is correct, right? And the same thing for Z2 and so forth. And what that gives is, if you look at the last proof, it says, hey, this last step was correct and it was computed with some previous proof. And then you can sort of like work your way back. Oh, if there was a previous proof, then there was a previous step and so forth, all the way back to the beginning of the computation. Yeah. And if you're thinking of this from a virtual machine execution perspective, then it will look like, essentially, this will be a function that executes the virtual machine, right, according to the spec that it has, and probably take many of those steps in one batch, right? So you'll do 1,000 or 1,000,000 cycles in each of these steps here. And the starting input could be like the program and the inputs, right? The output in the end could be the output of that program. And then you would have some create the corresponding proofs in the zkVM, and it will spit out a proof in the end, so you can know that the whole sequence has been computed correctly and you've got the correct. Okay. So okay, so the way it typically works is a little, I mean, so there's a bit of like massaging of the data to sort of like make this work. So I'll just quickly explain that. So for instance, one trick that people often use is that instead of giving the full program and input and so forth to the zkVM, maybe instead you'll just give a hash of those and sort of like loading. So we just want to make sure that you get the same thing as the hash, right? So sometimes you would compute this kind of like digest of the input rather than starting just with the input, and you would give that as the starting point for the VM. And then in the steps, you would sort of like feed in and say, oh, by the way, yeah, this was a hash of this program and this input. And then you will have the system up and running. And maybe in the end, you're not actually outputting the output Y. Maybe also Y would be part of the hash. It's going to supposed to hit Y in the end. And what you do here is just to check, oh yeah, did I actually hold and accept that now everything's good. And sometimes, okay, also you may want to massage this, so like the proof. So maybe it's one type of proof that is used by the incremental verifiable computation. And maybe what you really want in the end is a proof that you can put on the Ethereum blockchain. So you do some massaging and here, and you'll get that kind of proof up.
That's how we get the zero knowledge, but
indeed, yeah. So that's
Yeah.
also like, yeah, this last part is typically quite easy to make a zero knowledge proof. But with the caveat that this is still a question of what the nodes that are running the system have seen. Okay, so I want to dig a little more into, so like, what is the core problem, right? And the core problem is that, okay, so we implemented Nova, we did this, and we found out that the memory checking, it was an enormous cost what we're paying in each step, and that's so like from memory checking. So what is the problem here? Okay, so here's the naive way of thinking about how should I maintain memory, right? So we have zkVM, it has like a specification of what should each instruction do. So think of that as the CPU, right? And then it has some random access memory, right? Okay, so the naive thing would be, okay, let's the state be the memory, right? So like the setting of the CPUs, what are the register values and so forth, right? And then we run it and it updates the memory, it updates the state. And the problem here is, of course, that the memory might be really big, right? So now you have like a really heavy state transition function, which is expensive and unnecessarily expensive, right? There might be many of the memory addresses that we're not even using for anything, right? So they're not touched upon, but they're still in the state and you have to carry them over. And a natural solution to that would be to externalize the memory, right? So instead of doing that, why don't we just run a step function that handles the CPU and we just feed in what is the memory access. So if I want to access address number 3, right, it will say, hey, you're reading at address number 3, and that's the value in address 3 right now. And the same for writes, it would say, hey, the write is actually, after write, it should be a 7, in that is the value in this address, right? Okay, so that's sort of like a very natural idea, right? And so like the same as in computer systems, right? That you separate the CPU execution and random access memory. Okay, and that's great because now you only have to pay for like transitioning the CPU state. Now we just have the register values or whatever is the state of the CPU, right? But we're not paying the full cost for maintaining the memory in each step. So this is something like the zkVM prover has to keep track of externally, right? But that's cheap because it's not cryptographic operations anymore that we're using for that. Okay, so if you plug that into an incremental verifiable computation, it looks something like this, that you have the various memory accesses that we now give as auxiliary input to the CPU, right? It produces an output, it produces a proof, and everything is great, except you can fool the system, right? And the problem is that if you have a malicious zkVM, it might simply cheat with these memory accesses, right? So it might be, at this point, the CPU thinks it's writing some value to a specific address. It might be in the next step that it thinks it's reading from that particular address, and now we're giving it a different value as the input, right? And corresponding, the output might be wrong, but the proof looks great, right? Because the proof doesn't see that, it only sees that the CPU is executing correctly. Okay, so this is a problem that people are well aware of, right? And the question is, okay, then can we do some sort of like memory protection for the CPU? So roughly the idea is that you will split the virtual machine into two parts. One is the CPU part, but then there will also be sort of like an execution part that first takes as input the memory and checks that it's a correct memory access. And only if it's a correct memory access will it feed it further on into the CPU. Okay, so the question is then, how can we implement some system that does this kind of checking of the memory? Okay, so we want to have some system such that we can feed in like checks of the memory, and we would want the prover here to check that in every step. Okay, and the first idea that comes to everybody's mind is that how about doing Merkle commitments to the memory, right? So the idea is the following, that to start with, we'll have a Merkle tree that in the root of the Merkle tree that is hash would be what we feed as state to this, the virtual machine. And then whenever we access memory, we will give also a path to the root of that Merkle tree to verify that it's correct, right? And the memory checker will explicitly check that path and see, yes, indeed, that was the value at that address, right? And then whenever we have like done some execution, the memory will have changed. So we will output the updated root of the memory as so like the input to the next step. And then that can use that to check memory accesses and so forth. Okay, so that is great. It works, but it's horribly expensive, right? And that is exactly the issue that we run into with the first version of our machine. So like you have like, of course, a logarithmic number of hashes for each of the memory accesses that you need to verify. And you need to verify the inside the zkVM, right? So it's not like you just do some hashes, you're actually proving something about those hashes, which is really expensive. So you're paying like thousands of constraints for this. To be concrete, I think it's 30,000 constraints we're paying for every memory access, right? So it's like huge.
It's 3 memory accesses per cycle.
Yeah.
10 code for each. With the side as a hash function.
Yeah. So that's super expensive. Okay. So the question then is, okay, can we do better? And let me just see how I am for time.
Another question here, since you're recording some numbers, what's the address space size that you have in mind?
This for this is actually 2 to 20, which is pretty small, right?
Yeah.
I mean, we would like it to be 2 to 32, but
Yeah. The difference between reads and writes.
reads and writes? No, it's in this like memory checking mechanism, it's the same problem, right? It's just like a numerical fact. So about 20 hashes per memory address. Yeah, pretty basic.
Yeah.
Right, no, but I mean, it works.
Okay, so the cost here is enormous. So what I want to show is so like a different technique for doing memory checking, so like which is much more efficient. They actually have two techniques, but I think I'll skip one of them just for the sake of time. But here's a little bit of background that I'll need that so like is used in both of those techniques. So this in itself is not efficient, okay? But it's sort of like a mental model for what does it mean that memory is consistent. So because we want the zkVM to convince the verifier that the memory is consistent in its access all the way through, right? So whenever you read something, it should be the value that was last written, right? So what kind of constraints do you have in the system? And one way of getting consistency is to keep track of all the memory access you have, like the reads and the writes, and keep them in two separate sets. So there's a read set and there's a write set. Okay, and the invariant you want to keep out throughout is that the read set is behind the write set. So it's always so like one step behind in each memory cell, right? So you have written something and later on you read that, and until you're reading that, you're sort of like one step ahead in the writing. So you start with initializing the write set with, say, maybe you initialize the whole memory to be zeros in it. And then you'll keep track of the time and increment as you go along the computation. And whenever you want to access memory at a specific time t, you will find the latest write to that memory. Okay, so in the write set, which is not yet in the read set, okay, you'll check that it's in the past. If it's a reading you're doing, then you should also make sure that the value v is the same as the old value, okay? And then now you'll say, okay, now I have read that value, so you'll add it to the read set. So now the read set has caught up with the write set for this address. And then you'll write to the write set again. So if the read, you'll just put the old value, but you'll sort of like read them with it, write it with a new timestamp. So it's like refreshing the memory at this point in time. And if it's a write, then you may put a different value in there. Okay. So that way you sort of like keep track of the memory throughout, and this guarantees that it's actually consistent throughout. And then when the program is done, you would actually do then a final, so like add something to every read set to balance out those two sets. And then the guarantee and what you need for the memory to be consistent is essentially if the read set at that point is the same as the write set, then you are happy and you know the memory is consistent. You can sort of prove that if you're not cheating in any of these steps here, then that is actually enough to ensure that the memory is consistent throughout. Okay, so let me jump through this technique here and jump all the way up here. So I want to now use this notion here as part of a solution to give you really efficient verification of memory consistency throughout the computation. So remember, we have like the read set and write set. They have these kind of like tuples of address and value and timestamp, but they may appear in very different order in the execution, right? So they may be so like different from each other. Okay, I'll assume we have some easy way to map this kind of tuple down to a field element. So I'll just think of these as the read set as a number of field element values and the write set as a number of field elements. Okay, but they might appear in different order. So they're supposed to be just the same, but in different order, potentially. Okay, so there's a nice theorem dating back from Becken and others, and also concurrently in a work by Haberg that says that this is actually a permutation. So these R values is a permutation of the W values if this equation holds as a formal fractional polynomial. Okay, and the standard way of using that, so this is a well-known technique, it's been used in many proof systems, and the standard technique is you use Fiat-Shamir, you pick a random field element H, you plug it into this equation here, sum everything up, and make sure that they balance. Okay, so what's the problem? The problem is that when we do incremental verifiable computation, then this is not so easy to do, right? And there's sort of a couple of reasons that it's difficult. The first problem is that since we're doing incremental verifiable computation, right, we'll sort of do one chunk first, then the next chunk, then the next chunk, and so forth, right? So there's a bit of question, when do we decide on what is this challenge H, right? And it has to be present in the first chunk because otherwise we can't use it to actually plug it in and prove things. But the problem is if it's available in the first chunk, then we know it when we go to the second step, right? And then it's not much of a Fiat-Shamir challenge anymore. Now we can cheat. The second problem is that when we do incremental verifiable computation, then again, each of these steps will only have access to sort of a slice of what's happened, right? It doesn't ever, no step knows the full memory. That was the whole maneuver that we did. Right? We tried to make sure that they only see their own memory access and not the full memory, right? So then the question is, okay, who is actually going to do this summing up, right? Okay, so let's try to solve that problem. Okay, so we've sort of split up the step function, right? So the question is, how can we do this memory checking so we know that it's consistent throughout? Okay, and the important observation here is that the execution trace is actually independent of the challenge, right? Regardless of whether we have trying to prove things or not, we have specified the VM, it can just run the execution throughout, and we know what is going to happen throughout. We know what all the memory accesses are. Okay, so then the idea is let's first do a pre-processing step where we run zkVM prover to get the full view, the execution trace and what's happening. Okay. And all the memory accesses will be part of that. At that stage, we know all the memory accesses. And then we will commit to those memory accesses. Okay, so we'll commit to all the memory access in every step. Okay, and second, we will now compute a challenge that we're going to use. Okay, and we'll do that via hash chain. So we'll basically take first commitment, we'll have some starting point for the hash, we'll hash it. We'll hash in the second commitment and so forth. And at the end, we'll get some final output of this hash chain. And this is what we're going to use as the challenge. Okay, so why are we computing in this particular way? And the reason is that this is something that we can actually verify along the way. So what we'll do when we do incremental verifiable computation is we will give the challenge as input in the first step, right? We've sort of run first and pass through. We've got the challenge. Now we're feeding us an extra input to the incremental verifiable step function. And in each of these steps here, we will then say, here's a commitment to the memory accesses. And then this memory checking function can compute the next step in the hash chain. Okay, this is pretty compact. That's just a hash function. This is a small commitment. It's a fairly cheap operation to compute the next step in the hash function. So even though we're doing it inside and we're proving that it's correct and it's expensive to do things that we have to prove things about later, this is still manageable cost.
Why do you need to reuse the H for every step? Why can't you just have a different HI for every single step and just hold it that is directly included? For example, using this thing for special samples.
Oh, so you're asking why I cannot use a different H in each step to prove?
And
Yeah.
the itself without going into this.
Yeah. So the reason I cannot use a different H is because I want to make sure that, and I'm going to get to that on the next slide. But basically, the problem is that if you're using different H's in each step, then you don't get global consistency across all the steps. So you would sort of like get locally, you could use that to prove things are okay, but it wouldn't give you the global consistency. So I'll get to that on the next slide. So I hope that will sort of like be clear, get clear at that point. Otherwise, do ask me. What I want to get to at this point here is that we are actually recomputing the whole hash chain. It's a fairly cheap. And that the final step, now we get actually this H, right? And we can check, did I really get that H that I was supposed to get, right? And in that case, I conclude this is a correctly computed challenge. Okay. And since it's been computed as like hashes of all the commitments to the memory access, it means I can also not change the memory accesses anymore. Now they are locked in. Okay, so how are we going to use that? So remember, we wanted to use this lookup test here, right? So now I'm going to use this challenge that I have just recomputed and ensured is correct. And that's what I'm going to plug in here. Okay, so we verified that H is a correct challenge. And now the remaining question is, okay, just how do we get these sums out, right? So we have some sums over the reads and we have some sums over the writes. Okay. And that's sort of like the easy part of it. You basically keep track of partial sum, right? So in each step, you'll say here are some of the sums, okay? And add that to a running sum. And at the end of the day, when you get all the way to the end of the increment of verified computation, you will have those two sums. So that's what I have on this slide. So you'll start like with the sums, that are 0, and this will be like the initial values. And then you would basically do the lookup sums in each of these steps. And at the very end, you would have this sum and you would have this sum, and you just need to check are they identical. And if they are identical, you know that all the memory accesses are correct. So like a distributed computation of the standard technique to prove memory consistency.
What's the assumption on the hash function here? Presumably collision resistance is not enough.
I mean, it's sort of like a Shamir type of assumption you have to make it on. I think collision resistance is actually enough because that will guarantee that you're committing to all the values. You could do a trick then at the very end when you have like, you make sure that everything's collision resistant. Then you can apply a more whatever complicated thing you think gives you like a random oracle type of properties, and then you make sure that you're both binding to everything, and you also get the like the randomness that you want. Okay.
And actually, what happens if you have if the proof is actually constructed distributed by a bunch of parties? In some sense, you have to run through the computation twice.
Exactly. So it's a two-pass construction. Yeah. And I think this is the last one. So this is like a bit of like overview of the advantage and disadvantage, but because there's a bit of cheating going on here, right? So if you did the hash merging past trees, then it's expensive, but it really is just IVC. You can like start and then you can just get going. And actually, when you do the two pass, you have to choose in some point that like, this is where I'm going to stop. And this is like the first pass, right? So it's not really incremental verifiable computation anymore in the sense that you just keep on going, right? For that, you would have to do other massaging kind of tricks. So that's sort of like the downside. And I think from our perspective, right, I mean, it's sort of like, yes, that's a downside, but we care far more about the efficiency. Right now, we're going down from 30,000 constraints, right, to a small constant number of constraints per memory access, right? So that's a huge win. So, okay, and with that, I'll conclude the presentation. Thanks, guys.